Okay, so this is Wakaram Ashraf, and I am a first year PhD student at Department of Chemical Engineering, University College London, and my supervisor is Professor Vivek Dua. Today, I will be sharing my talk on the topic machine learning for operational excellence of industrial complexes, supporting the net zero goal. I would start to present the background for utilizing the machine learning for this large topic is like there is a rising pressure on the industrial community to operate their industrial complexes more efficiently and with less thermal energy spend and with reduced emission discharge to the environment. To this end, the operation managers and engineers, they visualize their hyperdimensional systems, operational data. They make the 2D graphs between some operating parameters with the response variables. But the problem is this technique for finding out some optimal operating points for the hyperdimensional input system could be suboptimal or not really good for estimating good operating point because the system is highly hyperdimensional and it has large input operating space. So to this end, in order to make this process more efficient and more reliable, industry has an opportunity to utilize this opportunity this space for enhancing their operations with respect to data they have in their data stores. So data is basically stored with respect to the operation of the industry in the data banks, and that data is basically representing the key characteristics of their industrial operations. And this data is basically available for corresponding to all the operating points, which and from the sensor which are installed corresponding to different measuring points. Another background which I would like to share with the attendees is that the operation of the large industrial complexes, it can be categorized into three levels. So one is the component, one is the system, and one is the strategic level. And the performance measures which are taken correspond to three different operation levels. They are either quantitative or the qualitative nature. Quantitative mean when the data is highly nonlinear, it's quite noisy, and it's very difficult to model this system. And qualitative is when the system is not really complicated. The data or the operating parameters with respect to the level operation and the data they have stored is not really complicated. So this is how the nature of the problem can be categorized into quantitative and qualitative. Another problem for using machine learning algorithms for making the models corresponding to the quantitative or qualitative nature of problem is the right choice of model they should have, because each model cannot fit across all level of problems. So the choice of machine learning model is really important. Another problem which need to be addressed with respect to developing a systematic and generic methodology, which can be utilized for making a systematic analysis framework for making informed and knowledgeable decisions for enhancing the operation management of the system. This is also lacking in the literature. Similarly, supporting the energy efficient operations is quite critical to contribute to net zero from the electrical power generations, because only coal is the only entity which is causing 40% of global CO2 emissions from the power generation. So this is how, if we have quite a big opportunity to improve the operation of the power generation system. So the thermal energy spent as well as their fuel consumption, it can be reduced. As a result of that, energy efficiency can be enhanced. So this is how I would like to extend my discussion towards the motivation of my study is to exploit the true potential of machine learning algorithms for the large industrial system and the big check industrial customers, which includes the oil and gas sector, process industries, power generation systems, to develop a framework which can be deployed at any type of industrial systems and to contribute to the net zero goal from the energy sector. Another motivation for us is to deploy the machine learning algorithm for the true potential, for exploiting its true potential. Because in the past, the machine learning algorithm, they are basically utilized for most of the times like lab scale or the pilot scale data. And the industrial community, when they have the large industrial complexes, their system is somehow different with respect to lab scale applications. So this is how the findings we have from the lab scale system, they cannot be directly implemented to be large industrial complexes. This is how the industrial community is not really, comfortable in utilizing or in to consult with the findings which are based on the lab scale control data of systems. So we actually wanted to demonstrate the true potential of the machine learning algorithm for the big tech industrial customers. So I will be explaining my finding on this topic in the coming slides. So there are a number of challenges which we need to address for deploying the machine learning algorithms for the performance enhancement of the large industrial complexes. And the first major challenge is the identification of the relevant input variables for modeling the system. And in this regard, the domain knowledge of the given system is really important to identify these relevant input operating variables. And we can also conduct a literature survey as well. Outliers removal and the input data visualization space is the second most important challenge which needs to be addressed very carefully, because the outlier, they may make the model prone to underperform or poor performing modeling results. And the input data space visualization is also quite important, because if the data is really distributed in the operating range with ideally it should be uniform, but the good distribution is present in the operating range, then we can have sort of more better training for the model. If the data distribution is quite poor, then the results from the model, it would be not really good, useful for making some informed analytics. The third important point is the selection of machine learning models, and they should be corresponding to quantitative or qualitative nature of the problem. Sensitivity analysis and domain-specific experimental design, which should represent the operational scenarios. This is the very important point when we are going to deploy the model for creating the value for the industry, because the experimental designs, they should comply with the operational physics, how the industry is operating, what are the operating scenarios. So in this end, the domain knowledge is really important for the machine learning engineer, so that the true value can be created for the industry. And the very last point here is the experimental validation of the results which we have developed on the real system, and then calculating the improvement in the strategic level performance measures of the industry. Here we have the methodology we have utilized here. The first step here is to take the data from the system, and then we have to visualize it. In the visualization, we are basically visualizing the outliers, the fault values in the data set, as well as the missing values as well, which need to be removed or addressed carefully. And then the data distribution space for the input and the output variable should be visualized. Here I have presented one example where I have 7 input variables, and I can see that the data I have taken for my 7 input variables, it is more or like uniformly distributed for most of the parameters between in its operating range. And in this one, the data is distributed from around about 300 to 660 value. And once the data visualization has been qualified, then the model, it should be made corresponding to the component, system, and strategic level. So the choice of the model should be made very carefully here. For component level problem, we have observed that the functional approximation models, they can be more a good choice. And for strategic level problems, the support vector machines or extreme learning machine, they can be a good choice, because they at strategic level, the data is not really quantitative. And thus the classification types of models, which are now working as the regression type models, they can be used for this one. Once the model has been constructed, the model should be validated on the system. And then the domain knowledge driven experimental designs or the operating scenario should be constructed, which should be simulated from the model, and based and they can be a lot of different scenarios. And then the findings should be verified on the system, and then we can compare if there is some improvement in the system in terms of thermal efficiency improvement or the thermal energy spent. Then we can indicate, okay, now the strategic level performance measures, they have been improved. Here I have represented 3 problems corresponding to component, system, and strategic level. So bearing vibration, the emission discharge from the flue gas system, flue gas desulfurization system, and the power plant heat rate, they are the problems, and the input variables, they have been identified. These variables, they are identified based on the domain knowledge as well as the literature survey we have conducted. And the second step is the data, the data cleaning, data outliers removal to ensure the operating range of operating parameter, and then the data visualization space, which is more like the just to see how what is the distribution or which distribution curve is being followed for my data. And then is the systematic cluster analysis, for which we are using self-organizing feature map to see how many clusters we have in our data set, to just evaluate the diversity of my data. Now the very next point is to the choice of the identification of the nature of the problem and the machine and the choice of the model. We have analyzed that the component level problems, they are of quantitative nature, and thus the ANN model can work better. Similarly, for strategic level problem, where we have thermal efficiency or the power generation from the power plant, there the S4 vector machine or ELM models, they can be a good choice. So this is how we started. This was our initial intuition. We although developed ANN model for strategic level problem and sport vector machine model for component level problem, but we found that the ANN model was working better for component level and sport vector machine was working better for strategic level problem. And here we have represented the model development phase, where in case of artificial neural network, the hyperparameter, they are optimized from 4 to 10, which are the hidden layer neurons. And the R-square value and root mean square error is represented here. So we can see that at hidden layer, when there are 9 neurons in the hidden layer, R-square value is approximately 1, and the error is root mean square error during training phase as well as during the testing phase. It's quite comparatively minimum compared to the other networks which we have constructed based on the hidden layer neurons. So this is how we just optimize the hyperparameters. And then we validated our developed model on the system. I just want to mention here that I have mentioned a few results here because I had 3 problems. So different, some representative graphs I have taken corresponding to different problems, so that just to make it a bit simple and avoid a lot of graphs here. So here I have shown the validation graph for my ANN model, and here and this is the external validation results when the model was deployed to validate the validation data set. So we can see here the relative error is less than 2%, and there is a good comparison between there's a good fit between the actual and the predicted value between the ANN model and the actual model here. So once the model has been ready, so the very next point is to have some insight about the system, for which this purpose we have used, we have deployed the sensitivity analysis algorithm for getting to know which is the most significant input parameter. And for sensitivity analysis, partial derivative method and Monte Carlo randomization technique we have used in our results. And here I have shown the impact of this relative significance of my 4 input variables on the power generation here. And for this one, when we have the parametric significance analysis, the impact of input variables on my output variable, it has been shown here, and as well as the recommended operating ranges for the parameters, they have also suggested here. So now, when we develop some optimized results based on the analysis, we found some, those findings, they are validated on the power plant in order to see how good these results are. So these are the validation results for the bearing vibration, which was the component level problem, and these are the validation results for the power generation from the power plant. And the results are comparatively, they're good in terms of controlling the system into its operating ranges. So which basically demonstrate the good modeling performance of the model, as well as the good optimized result which we have obtained from the model. And based on the performance, the experimental verification of my model, when the system efficiency is improved, we have computed some operational excellence measures corresponding to the power generation under 50%, 75%, 100% operation mode. And we find that the thermal efficiency is improved from 39 to 40% under 50% power generation mode, and the fuel consumption, it is also improved as the result of the improved operation setting of the parameters. So based on the improvement in the thermal fuel consumption rate, we have computed the reduction in the emissions corresponding to different power generation modes. And so these two graphs are basically showing how much emissions they have been reduced as a result of the improved or the reduced fuel consumption for the power generation. So to conclude with, so there have been a number of challenges which we have identified in terms of data collection, visualization, processing, model development corresponding to nature of problem, development of the domain knowledge-driven operating scenarios, and the simulation verification on the model. So these challenges have been addressed to demonstrate the true modeling capacity of machine learning models for the large industrial complexes. We have identified that ANN model, it may work better for quantitative nature of problem, which is the components and system level, whereas the SVM and ELM model, they can model better the qualitative nature problem. We have performed variable significance analysis and the extensive parametric study based on the model. And then the findings which we have obtained, they are complying with the domain knowledge, as well as they have been used to make the informed decision making, as well as the operating scenarios, which I have discussed before. The machine learning model simulated findings are then validated on the real operation of the power plant, and the significant saving in fuel consumption and improvement in the energy efficiency and significant reduction in emissions, they are achieved. And these findings, they have been already reported in our published results, published papers. So for the future work, we are basically planning to deploy the machine learning algorithms for the modeling the power generation from the fossil-based power plant at the global scale. And then we wish to quantify the performance enhancement measures, like in terms of the energy efficiency, thermal efficiency, emission reduction potential under uncertainty for the global scale, so that we can demonstrate how much potential it exists to operate the existing fossil fuel and based energy assets, so that the emissions, which is the primary factor to contribute to net zero goal, if they have been reduced, so we can contribute towards the net zero goal from the energy sector, or in general industrial complexes, based on the reliable and robust utilization of machine learning algorithms. So this has been the discussion from my side. So if anyone has some questions, so I'm very happy to discuss about those queries.
Okay, thank you very much for the presentation. Maybe we have one or two questions from the floor or from the audience. Yes, please.
So in the presentation itself, what although it was a nice presentation and the data and comparison also good, I wonder how it is, because the thing is that the data that you have taken, maybe it may be not consistent throughout the year. Say for example, we are taking a PowerPoint, so the power requirement throughout the year is not same as in some of the parts of the world. Right, in the winters, maybe we may require more energy for the heating applications, and sometimes in the hot regions of the world where the summers are very hot, so there a lot of energy is required for the cooling systems. So how your this developed model is going to work on both the scenarios?
Yeah, I agree. I see your point, and this is a very valid question. So I would like to mention here that the data I have is basically from the power plant which is installed in my country. But I think the seasonal fluctuation in the power generation, it is basically it is available in everywhere. One thing, and the second thing is this is the study which is for one power plant. When we have the data from the global scale, then we can say, okay, this model can be deployed for for the applications at the global scale. But specifically, this model is for one power plant. And second thing is the coal power plants. They are basically used for base load power management. In that case, there is basically fluctuation in the power generation, which is depending upon the frequency stabilization of the national grid, but still there exists energy fluctuations. So considering the coal power plants, they are the baseload power plants, and they follow the similar type of fluctuation. So this can be used for making some predictions and then making any sort of analytics which industry managers want to make. Yeah.
Okay, is there any other questions? No? If not, I think let's give him a warm applause then.